Commercial aviation burns through roughly 100 billion gallons of fuel a year, leaving a massive carbon footprint in its wake. The aerospace industry has spent decades searching for a viable way to cut those emissions to zero. Electric batteries are often the first proposed solution, but they carry a severe weight penalty. To power a commercial long-haul passenger jet, the battery packs required would be so heavy the plane would never actually get off the ground. This scale illustrates why engineers are looking toward hydrogen. A tiny amount yields the same power as a massive cluster of heavy batteries. But this energy density brings logistical hurdles. Highly volatile, storing hydrogen requires extreme pressure just to manage it safely. Because of those explosive risks, aerospace engineering has historically kept hydrogen tests strictly limited, running partial simulations or using highly diluted fuel blends to avoid hardware failures. That cautious approach has ended. Rolls-Royce, working alongside Britain's health and safety executive, has successfully run a modern aero-gas turbine jet engine at full takeoff power using 100% pure hydrogen fuel. By completing this ground-based flight cycle, engineers have demonstrated that zero-emission commercial aviation is now a proven technological reality. Feeding a highly reactive gas into a massive commercial turbine without triggering an explosion requires an entirely new type of ground-rate infrastructure. To build it, Rolls-Royce brought in Britain's Health and Safety Executive, or HSE. Their specialist research team has spent over 20 years working directly with complex hydrogen systems in demanding industrial environments. Together, the scientists and engineers designed custom high-flow, high-pressure delivery mechanisms, pairing them with extensive digital monitoring systems to regulate the exact amount of gas entering the rig. This safety-led engineering provided the precise control needed to tame the fuel, serving as the foundational tool for testing one of the most volatile elements on Earth. Inside the engine, pure hydrogen ignites more aggressively and burns at different parameters than traditional Jet A kerosene fuel. This animated schematic details fuel injection valves, calibrated to handle rapid combustion without stalling the turbine. With flow stabilized, researchers spooled the turbine up, pushing the combustion rate until the digital thrust output held at the 100. The team throttled power down to simulate cruising altitudes, holding the turbine at operational speeds. Mid-cycle, researchers introduced intentional fault scenarios to see how the active engine handled sudden mechanical anomalies. The custom monitoring systems detected these irregularities immediately and automatically adjusted the hydrogen flow, preventing a stall and keeping the turbine running smoothly. Surviving these stress tests confirms that hydrogen provides the explosive lift for departure and the steady, reliable endurance needed for hours of high-altitude travel. The data collected from the Engine GH2 rig has given aerospace engineers the clearest, most detailed understanding of hydrogen combustion ever recorded. Interestingly, many of the breakthroughs regarding system monitoring and fault management apply to engine efficiency regardless of what is actually burning in the chamber. Rolls-Royce is extracting these insights and integrating them into the design of their future commercial aircraft engines, specifically the upcoming UltraFan project. By translating theoretical chemistry into actionable, hard data, this simulated flight has immediately shaped the engineering blueprints for the next generation of aviation. Aerospace companies and governments worldwide are racing to hit strict net-zero emission targets to secure the long-term future of everyday commercial travel. The heavy involvement of the HSE proves that enforcing rigorous safety standards early on validates and accelerates green innovation. Hitting full power without incident effectively de-risks hydrogen as a viable fuel source, providing the empirical proof that regulators and investors demand. This successful test transforms the concept of zero-emission hydrogen flight from a theoretical model into the definite future of global transportation.